Today's topic is pulse transfer function. For a linear time invariant continuous system, we can define the transfer function that describes the dynamics of the system as g of s is equal to c of s by r of s. This is the transfer function for continuous time system. To this system, let us assume that we give an impulse input which is defined at t equal to 0. Let us consider the system as a second order underdamped system. We can see that the output c of t will be a continuous one as shown in the figure. This continuous output is obtained for an impulse input just because the process is a continuous one. And we consider another case where an impulse train is given or a pulse train is given, which is defined only at regular intervals 0, t, 2t, 3t, etc. We can see that the same is the case for pulse train also. The output will be a continuous one. It is just a repetition of a number of impulses that happens at regular intervals. So, if the output happens to be continuous one for just one impulse, so is the case for impulse train too. Now, we move to the derivation of pulse transfer function. Let us assume we have a continuous time system g of s to which an input r of t is sampled and given. The sampled input is given by r star of t. As discussed, when you give an impulse train, we can see that the output will be a continuous one. So, if you give a sampled input also to a continuous time system, the output c of t will be continuous. But people thought of considering the input-output relation only at regular intervals of time capital T. So, if this is capital T at regular intervals, that is, let us assume that sampling happens at regular intervals, if one wants to find the input-output relation at the same regular interval, then in the absence of a sampler at the output, one can place a fictitious sampler at the output that opens and closes at the same regular interval as that of input, and we can call the output as c star of t. This means that we consider the output only at regular intervals capital T. So, an analysis of such a system can be done as follows. Here, let us write the Laplace domain representations. R of s, this will be r star of s, c of s, and this is c star of s. C star of s is nothing but the Laplace transform of c star of t. So, if you consider the above block diagram, we can write the following relations as c of s is equal to r star of s into g of s. But since we are interested in the relation between c star of t and r star of t, that is a sampled output and a sampled input, we need to consider what c star of s is. So, c star of s is nothing but the sampled c of s. So, that is equal to r star of s into g of s star, and this is r star of s star, so that is r star into g star of s. And here we can see that once sampling is done, then whenever you sample it again and again, the same samples will be obtained. That is why r star of s star is equal to r star of s. If you keep on sampling again and again, we get the same thing. So, c star of s is equal to r star of s into g star of s. And we can see that c star of t is nothing but c of kt, because it is a sampled values. by definition of Laplace transform of C of t is given by integral 0 to infinity C of t e raised to minus st dt. Since it is a sampled signal, C star of s, that is Laplace transform of C star of t, can be written in the summation form as sigma k equal to 0 to infinity C of kt into e raised to minus skt. If you substitute e raised to st as z, then we can see that this is nothing but sigma k equal to 0 to infinity C of kt into z raised to minus k. So that is nothing but C of z. So C star of s is basically the z transform of C of kt. That is, C star of s can be easily replaced by C of z. So if you look at this equation, we can write C star of s is equal to R star of s into G star of s. Hence, C of z is equal to R of z into G of z, and C of z by R of z is equal to G of z. This is pulse transfer function. So, pulse transfer function is the ratio of the z transform of the output, that is the sampled output, to the z transform of the sampled input. In doing so, the output information between the sampling instance is lost. Next, we move to the points to be kept in mind while dealing with samplers. So, the first point is a signal R of t, when sampled once, we get R star of t, provided the sampling instant is capital T. If this signal is again sampled at the same instance, then this will be R star of t star, that is R star of t itself. This was discussed in the previous slide. The second point is G1 star of s into G2 of s star will be nothing but G1 star s into G2 star of s. The third point is, if you don't have samplers in between two blocks, and if you try to find the sampled signal of the combined one, then this can be written as G1s G2s star, that is G1 G2s star, and but this is not equal to G1 star of s into G2 star of s. Thank you.